So, after writing that what is the mass going inside this control volume in x direction, y direction, z direction, what is the mass going outside the control volume in x direction, y direction and z direction, we can write the conservation of principle. Conservation of principle. So, we can find out that what is the mass flux in x direction. To find out what is the mass flux in x direction is equal to what is the mass going outside the control volume in x direction is equal to rho plus del rho over del x into dx multiplied by u plus del u over del x into dx into area. This is the mass going outside the control volume in x direction. So, if we open this bracket and neglect the higher order term, we get this term, right. Now, what is the net mass flux in x direction is equal to mass going outside in x direction minus mass going inside the control volume in x direction. So, this much is the mass going outside the control volume in x direction minus this is the mass rho into u, this is u, rho u dy dz. So, this is the net flux in x direction. So, rho u dy dz, rho u dy dz is cancelled, we have del over del x rho u dx dy dz, right. Dx dy dz is the volume dv dash of this parallelepiped. So, del over del x into rho u del dv dash. Now, this is the net flux in x direction. Similarly, we can find net flux in y direction and net flux in z direction. So, similarly, we can get in y direction and this is in z direction. In y direction it will be del over del y rho v dv dash, in z direction it is del over del z rho w dv dash, right. So, accordingly, with the help of conservation of mass we can write that what is the net flux in x y z direction is equal to del over del x rho u plus del over del y rho v plus del over del z rho w multiplied by volume. This is the net flux. Now, if net flux is minus, it means that some of the mass of the control volume will reduce over the time, and if net flux is positive, it means that mass inside the control volume is going up. So, it means that mass density will also change over the time, which is written as del rho dv dash divided by del t, right. This is rate of change of density, right, del rho over del t into dv dash. Now, dv dash is constant for this chosen control volume, right. So, that is why it can be taken outside the control volume. So, we have this equation that del rho over del t plus net flux in x direction, y direction, z direction must be equal to 0, because no mass cannot be created and cannot be destroyed. So, dv dash cannot be 0, it means that del p over del rho over del t plus these terms must be equal to 0. In vector form, this may be written as del rho over del t plus del dot rho v vector is equal to 0. If flow is a steady flow, then this term del rho over del t, because we know if flow is steady, then properties, density or other properties, they do not change with time, they are independent of time. So, del p over del t will become equal to 0, then equation is reduced to del dot rho v is equal to 0. So, this equation may be expanded in a Cartesian coordinate framework in 3 dimension del over del x rho u plus del over del y rho v plus del over del z rho w is equal to 0. And if flow is a incompressible one, if fluid is a incompressible one, then rho is also constant. So, rho can be taken outside this differential sign, and this may be written as del dot v is equal to 0. It means del u over del x plus del v over del y plus del w over del z is equal to 0. So, this equation is in 3 dimension, but for steady and incompressible flow. So, if we have a steady incompressible flow, then continuity equation may be written as del U over del x plus del V over del y plus del W over del Z is equal to 0. So, this is a continuity equation is nothing but it is a conservation of mass written in terms of the density and velocity gradient of the flow region.